nuclear energy maybe seems a little bit scary because of, I don't know, I guess just kind of some just bad press.
Yeah.
But it's not scary. It's not different. I think, we were just talking about simple phase diagrams. It's a materials science problem just like any other alloy design.
Hey everyone, welcome to It's a Material World. We're the show that uncovers why material science will change the world. Consider subscribing and hitting the like button down below. It would really help us out. And without further ado, let's get right into it.
Hello, everyone. Our guest on today's episode is Dr. Liz Kautz, a material scientist at the Pacific Northwest National Laboratory, or PNNL for short, which is what we will call it throughout this episode. She specializes in researching the use of uranium, molybdenum, metallic fuels, and zirconium alloys, and is extremely knowledgeable about the even crazier world of materials science and engineering that happens in and around nuclear reactors. We're excited to have you on the show today, and welcome, Liz.
Thank you for the introduction.
Of course.
So my background on nuclear materials is very limited, so I wanted to start with the basics. What exactly are nuclear materials and what applications are they well suited for?
Nuclear materials is a super broad term, I would say, and also field. So I can just share sort of like what I think of when I think of nuclear materials, but of course, I'm biased by my education and my work background. But when I think of nuclear materials, I typically think of any materials that are used in nuclear applications, which might range from things like fission reactors to power the grid and provide electricity to, towns, businesses, etc. So commercial nuclear reactors, and have up and coming or under development fusion reactors. And these, so I typically clearly think of reactor and the materials that are in these reactors and allow these reactors to work and stay powering the grid, for example, for the fission reactors for long periods of time. So examples would be things like in the reactor core itself are fuels. We all know about uranium. Uranium is a fuel that is used in the core of nuclear reactors, but it's not just uranium. So uranium fuels are clad in, they're called cladding, and that's zirconium alloys typically, although stainless steels are also used. And so these are materials that are in the core, but then there's also the whole secondary side. So there are a lot of, non-uranium containing alloys, other like steels and nickel-based sorts of alloys on that side. So there's the whole range. There's a lot of materials that help make a plant run. And so this is kind of what I think of nuclear materials. But I guess I should also mention that it's not just about nuclear power. Certainly there's like stockpile materials such as uranium and plutonium. And so these are also considered, under at least my definition, nuclear materials, but with a different application.
Awesome.
Does that answer your question?
Yes, it does. I had a quick follow-up. So you mentioned cladding materials, and I think that might be something we get into later on, but can you briefly just talk about, what exactly are cladding materials?
Let's just take the example of a light water reactor. A very common fuel is uranium dioxide, UO2. And so these can be formed in pellet shapes. So think of really small cylinders stacked on top of each other. And then surrounding that is cladding. And those cladding materials, I mentioned zirconium earlier. Zirconium is a very common cladding material because it's what is known as neutron transparent. The neutrons can basically go, the zirconium is not going to suck up any neutrons, so they can get right to the uranium. So this is kind of the whole cladding material concept, where the cladding is actually the material that faces the water. If, we're talking about light water reactors where water is the coolant and moderator here. Does that?
Yes. Yeah, that makes sense.
Yeah. Zirconium is right next to the water's flowing by, and things like corrosion, materials degradation. These are all concepts that people care about very much when they think about cladding materials.
Awesome. So since there's so many things to consider, what makes you passionate about this field?
Yes, good question. So this kind of reminds me of when I was trying to figure out my undergraduate degree. I'll get to your question, I promise. Right. So when I was trying to figure out what the heck am I going to major in as an undergrad, I was like, every engineering discipline seemed interesting to me. But the two things that stuck out to me were nuclear engineering and biomedical engineering, which is a little bit, anyway, let's just table the biomedical engineering thing. Maybe that was a weird, phase. But the reason nuclear engineering stood out to me was because it seemed like an area that there was a lot of active research. I felt like the applications were very worthwhile, because I think, people are now considering nuclear more as like a clean energy source, although there is the issue of waste processing. But there are a lot of challenges, right? So there's the challenge of waste processing, and then maybe designing new reactors. And a central component of this is the materials aspect. So that's like stuck out to me as like this big challenge. And I said, okay, maybe I shouldn't like just focus on the nuclear engineering aspect. I should look more at the materials, because that seemed to be like the future and where the research was happening.
That's fascinating though. And so, for our audience, to give them some background if they don't know a whole lot about nuclear, what are the basic ingredients of a nuclear reaction? I think you've started to allude to a few of them, but, explicitly, what are those things? And in terms of those ingredients, what's the difference between fusion and fission as, in terms of what they require?
Sure. So I'll just kind of start with fission. The ingredients you need are, you need U-235, you need neutrons. And so when a neutron hits U-235, more neutrons are like produced. If you fission the U-235, and you create more neutrons, and those neutrons then go to hit, fission other U-235. And so the idea is that you need sufficient neutrons to sustain this reaction so that's like when your reactor is critical. So that's like criticality, or I believe is the correct term there. So these are like, this is the gist, right, of what's kind of going on in the core.
Right.
And I guess, one of my mentors once, or maybe it was at a talk, I forget, someone described a nuclear reactor as a tea kettle. All you're doing is, heating water. And that's, I feel, the best description I've heard. You're heating water, and that's what the core is there to do. And so you heat the water, and the secondary side has things like turbines and a bunch of piping so that you can generate electricity there. And the idea is that you kind of have two loops, primary, secondary. One has radioactive components or materials, and the other is kind of separate from that. So you're heating water, making steam, electricity, etc., on these two sides. What I do know about fusion is the idea is you need self-sustaining plasma. And this is a super important problem because we don't really know how to contain a burning plasma that's as hot as the sun. And, what materials do we use to do that? How do we, keep such like a extreme environment operational on Earth for so long? Like, these are kind of open questions in the fusion realm, to the best of my knowledge.
Yeah, no, it sounds like.
Does that answer your question?
Yeah, no, it's definitely one heck of a complicated problem to be able to solve fusion. But in terms of
it is complicated, and I'm certainly learning.
Yeah. Oh, yeah. It's one of those like grand future things that, at maybe 50, 100 years from now, they'll get it right. But in terms of the fission side, what are the current types of materials that are required to contain these nuclear reactions so they don't go and get to a state where they're not sustainable?
Sure. So I mentioned like fuel, cladding. So if you ever see like a commercial power plant, there's a bunch of different buildings. It's like it's like a campus, but kind of when you're kind of alluding to some safety measures. So this fuel and cladding is contained in a pressure vessel, and then there's a whole containment kind of facility that surrounds that. So there are a lot of different safety measures in place that kind of prevent anything, this reaction that's going on in the core. There's a lot of different things that are going on to control that. So some of those things include control rods. So I was talking about neutrons earlier. So neutrons will fission U-235, and how do you control? So, and one neutron fissioning one U-235 produces more than one neutron, right? So you get more neutrons than you put in. And how do you control this? There's certain additives to the water. So the water chemistry can help moderate this reaction, in addition to control rods that are kind of opposite to zirconium. Hafnium sucks up neutrons. So while zirconium is transparent to neutrons, hafnium will suck them up. There are other, control rod materials and ways, but if you think of like kind of, I guess, a classic pressurized water reactor design, you can kind of insert hafnium control rods into the reactor to suck up some neutrons to control this reaction. So that's, I think, a key aspect of controlling this reaction that you're talking about.
Cool. So you mentioned zirconium alloys, and you've worked with uranium molybdenum alloys. So what's the difference between these types of alloys that we use in nuclear reactors compared to more traditional alloys like we use in bridges and cars, like steel and aluminum?
Sure. Well, I will say steels are all over the place in nuclear reactors, but if we're talking about core materials, uranium and zirconium are there, and they're special. So uranium is special because of fissionable isotope U-235. So, and that's just the concept we were talking about earlier. It's fissionable, so neutron can fission U-235 and it produces more neutrons. So it's like not found in nature. If you mine uranium, you're not going to have like a whole chunk of U-235. You need to go through a lot of different processes to get uranium that's in kind of a form for fuel, which is enriched in this specific isotope. So that's special about it. And zirconium is very special because of, I would say, its neutron transparency. If you can look up things like neutron transparency for a bunch of different materials, and you'll see that zirconium is like exceptional in this kind of aspect. Steels will suck up more neutrons. Hafnium, I already mentioned, that's like, the other end of the spectrum that makes hafnium super special. And so there's that, I would say these are the two key aspects why people use uranium as fuel. Like that's pretty ubiquitous. And then zirconium also. And people have spent a lot of time since like the 1950s or so trying to take zirconium and alloy it in different ways to get the best possible fuel cladding material there is. And that is certainly an ongoing aspect of research in the nuclear industry. How can we make a zirconium alloy with, we can leverage the neutron transparency aspect, but also minimize the corrosion in, these relatively high temperature, pressure, and, maybe what you would call extreme environments.
Right.
Although someone who's working maybe in like, jet engines, not very extreme or whatever, but right. So I would say in the realm of zirconium alloys, pressurized water reactor cores, or some extreme environments.
Wow. Yeah, and it just sounds like some really intense engineering challenges to overcome to be able to do this sort of thing successfully.
Yeah, I agree with that.
And so, nuclear power sometimes gets a little bit of this bad rap. Notably, we've seen some devastating impacts of some nuclear meltdowns like Chernobyl and then Fukushima, which was almost a decade ago at this point. And so, how does your work at PNNL help enable a future in which nuclear energy is safer and more ubiquitous than it is currently?
Sure. Well, I would like to start by saying that I think there are aspects of nuclear energy that aren't as widely accepted as I feel maybe they should be, because there's a lot of like politics tied into that.
Right.
And which is unfortunate, because when you think about the energy density maybe not energy density, but the amount of energy that a single pressurized light water reactor plant could produce as compared, and its footprint.
Right.
Now think about a wind farm. Okay, wind farms are, I promise I'll make a point. The wind farms are like, I live out in Eastern Washington. If I drive to Portland or Seattle, I'm in the middle of nowhere, but I see a lot of wind farms. So this is interesting because there aren't that many people around, but there are a crap ton of, windmills.
Yeah.
So you have to take this energy that's generated at these remote wind farms, bring them to people. Whereas nuclear reactors are actually very, very safe. And they can, there isn't this massive challenge of transporting, electricity that's generated super far. And it's it's a smaller footprint. You don't have this challenge of transporting energy very far away. And the amount of energy that, can be produced just from a single fuel pellet or something is enormous in comparison to some of these other, green energy technologies such as wind farms, solar, and efficiency is very high. So I feel like there's a lot of, and I'm saying all these things and I don't really have numbers, off the top of my head to back them up, but I know this is true.
Right.
and I'm sure those numbers are available on the internet. But so I think the key to maybe how my work links to making nuclear energy more widely accepted. I mean, I'm not in policy, I'm not in politics, anything like that. But one of the aspects that is of a major concern, I think, to the public are things like plant materials degradation in the plant. That's an issue in things like core melt. Although I'm not studying, conditions that are, that would be experienced during a core melt. Understanding how materials behave in certain environments can enable a better predictive capability of how these materials are going to perform over the lifetime in a reactor.
Yep.
For example, how does the cladding material perform, in an 18-month cycle, multiple cycles, etc. So I think that's kind of how my work contributes, because if we understand our materials better, then I think, we can move on to improved plant designs, and that can make for a very strong case for maybe more and better reactors in our future. I think another aspect that I'm not actively working on now, but is very important, is this concept of waste management. A lot of people here are involved in that aspect of nuclear energy. I'm not per se, but again, that's a kind of a materials degradation problem. Where when we think about nuclear waste and a geologic repository, or even just like shorter term storage, what you need to think about is how can I safely store these, fuels or core materials that are radioactive in a safe way that it provides a barrier to the outside environment or the public, right? So when the concept of a geologic repository was, came up, I think design engineers or something, they were asked to design for something like 10,000, probably more, many thousands of years.
Yeah.
For these materials to not break down, which was like an enormous, crazy challenge, right? So I think any sort of research related to materials degradation, whether it's related to glass waste forms, metal canisters, ceramics, etc., this is all kind of still in the direction of how can we provide a safe method for long-term disposal of nuclear fuels.
Really cool, really cool. So let's dive into your work a little bit. What is it about uranium, molybdenum, metallic fuels that make them useful in the development of the future of nuclear reactors? Like, why are you working on these types of alloys?
Sure. Yeah, that's a good question. So I'm gonna step away from fission reactors for a second and talk about, so when I was previously talking about fission reactors, I was thinking about commercial reactors. Yeah. Power the grid, that's the goal. But there's a whole other type of reactors that exist in this country and also worldwide, research reactors. And the purpose of research reactors, there are several goals, but I would say the primary goals are first to test different materials in neutron and radiation environments, very typical of a real operating plant or an environment of interest that isn't easily reproducible in a small laboratory.
Right.
So it's a big testing facility, and also medical isotopes are produced there. So there are research reactors all over the country, and there's a special subclass of those called high performance research reactors. And in the US, those are things like there's a reactor at Oak Ridge, INL, MIT, Missouri, S&T, and I think there's 5, but I'm missing one. In any event, these are like the specific research reactors that this UMOLY, uranium molybdenum alloys are currently being developed for. So why these alloys is because previously or historically, these reactors are, as the name suggests, high power. They were using highly enriched uranium fuels. So highly enriched is defined by the NRC as anything over 20 weight percent U-235 relative to like all other uranium isotopes. And so you can imagine that there's some risk associated with continuing to operate these reactors with that kind of uranium enrichment. The risk comes, when I say risk, I mean proliferation risk. And you can imagine that, the same highly enriched uranium that's used in these plants is the same sort of material that could be used to make a weapon or a bomb.
Sure.
So there's a big push to reduce the use of highly enriched uranium. So we need to move to a different fuel source where we can also get, so a main goal is to get a high enough U-235 density in a fuel to maintain the same power requirements that these reactors are already operating at. And uranium alloyed with 10 weight percent molybdenum is a leading candidate for that. And the reason that, so I guess, if you say, okay, I want the highest uranium density possible, you would think, why not just have all uranium? So, this is what I thought, right? Or it's a natural question, I guess. But the reason molybdenum is added is to stabilize the high temperature cubic phase at lower temperatures. So,
interesting.
So it's a minor alloying. It's not minor. It's 10 weight percent. It's an alloying addition to do that, stabilize the cubic phase, because if you don't have a molybdenum addition, then you have an orthorhombic crystal structure. And when you're talking about, a fuel operating in a reactor, it swells. And so if it's swelling non-uniformly, that's a bad thing. So there are other metals that can be added. I believe uranium, niobium, uranium, zirconium are also under consideration, but the US currently is, pretty devoted to the U10 moly alloy. Does that answer your question?
Yeah, no, and I have or I believe it does, but I do have one follow-up to that, which is, or just to clarify, so you're essentially saying that the molybdenum stabilizes that polymorphic transformation in the uranium, and that if you go through that transformation, you run the risk of your fuel having some sort of degradation upon its expansion or contraction through that polymorphic transformation.
Yeah, so degradation probably,
or may not be the correct term there.
Right. Yeah. So actually, if you look at the UMOLY phase diagram, it's and you just go to the uranium rich side.
Yeah.
So below 565C or so, you have alpha uranium plus gamma prime. And above 565 or so, you have this cubic phase. But if you move all the way to uranium, no, you can't see that. So the cubic phase is only stable above this certain temperature in uranium. But if you alloy it with molybdenum, then you can retain it at lower temperatures. So yeah, that's the whole idea. I think that's also what you're saying. Yeah, it's a polymorphic transformation, and you want to avoid that alpha uranium phase.
Right. Wow. Oh, that's really interesting.
Just an alloy. I mean, it's actually, I remember when I first saw the phase diagram, I was like, oh,
that's it. Okay. Yeah, no, that's just like, it's so interesting that, I mean, we learned about polymorphism, fairly early on in material science. And like, It's just interesting that that's like one of the motivations for it is something that like is one of these fundamental material science principles. And, the other major element of your work is studying these zirconium alloys for, in terms of as one of these cladding materials. So, what is their role to play in the development of this next generation of nuclear reactors? And, what exactly is their purpose moving forward?
Sure. So, I mean, yeah, zirconium cladding still is kind of, the front runner in when you think of light water reactors. And right now, I think there's a big push in, these newer, kind of a newer era of zirconium alloys so I guess I'll kind of go back to 1950s or so. The series of zirconium alloys called zircaloys were invented or whatever. And so zircaloys are very dilute zirconium alloys. So dilute because you want to minimize any absorption of the neutrons, but you also want improved mechanical properties. And so it was kind of, what you would think of as a typical trial and error alloy design approach. And so the series of zircaloys resulted. So zircaloy 1, 2, I don't hear very much about zircaloy 3, but I'm sure it's there. Zircaloy 4. And so zircaloy 4 is very commonly used now. So I know the difference, and major difference between 2 and 4 is that nickel was in zircaloy 2, and then zircaloy 4, there's no nickel, a little more tin. So the reason that nickel was taken out was because it was correlated to an increased hydrogen absorption. So when people look at things like corrosion of zirconium alloys, they're very concerned with phenomena such as oxidation. So oxidation and hydrogen ingress and hydrogen pickup. Hydrogen pickup is important because when hydrogen and zirconium interact, and kind of, again, you can take a look at the phase diagram, brittle hydride phases can precipitate if you have a high enough concentration of hydrogen. And so that would be detrimental to things like the mechanical integrity of the fuel cladding, which is important because we don't want the fuel to directly contact the water.
Right.
So I think now I'm just talking a lot about zirconium alloys, so I'll try to get back around to your question. So your question was primarily about how does my research kind of relate, right, to the development of zirconium alloys and how that might enable, improved reactor design, et cetera.
Yeah.
So right now, my research in zirconium alloys is actually on the side of this hydrogen ingress that I mentioned. So something that I'm working on now is looking at how can we better map and measure the hydrogen picked up in zirconium alloys. So a lot of work has been done in this area, and I'm just kind of looking at it from an analytical perspective right now. I'm trying to compare different methods, because when you get, and the reason I kind of want to look at different methods, see how they compare, and kind of compare contrast sort of situation. The reason I want to do that is because when you get, say, cladding that's been irradiated through their hydrides, you can analyze these materials a bunch of different ways. But I mean, I feel that I would prefer to take more of like a tiered approach, where you start with larger scale chemical mapping and go down to nanoscale. And so that's kind of the workflow I'm working towards now. I want to, in certain materials, certain zirconium alloys with different hydrogen concentrations, how can I map using multiple different techniques the hydrogen from millimeter down to nanoscale? And and can I do that accurately? So not very application based, but I think the analysis portion is an important part. And so, and how does this relate to kind of, future is that anytime you can measure quantities, concentrations with higher confidence and better understand how it fits into the bigger picture.
So, so from the material science perspective, just taking it a step back, looking at it from a broader idea, what are some of the current challenges that you face in enabling your research and just in the nuclear space as a whole to have a broader impact on society? I know you mentioned waste processing is one of them, but just wanted to address those challenges again.
So you mean just in general, not necessarily in my research?
We can talk about like briefly in general and then kind of dive into, the challenges you're facing in your research.
Sure. Well, I think waste processing just happens to be like kind of a little bit more political, which I think sort of lead by saying, politics impact funding. Funding impacts research. That is everywhere, whether it's nuclear materials or basic. I don't know.
Basic science.
Materials. Yeah. Right. So I think that is a challenge that we will always face. I say we, researchers, whether you're at a university or at a national lab.
Right.
And I think that's a big one, especially when, you start to think about things like waste processing, where, a huge barrier there is, where is, as the US, where is our geologic repository going to be? Yeah. So Yucca Mountain was a thing, no longer a thing, like what's going on there? But who knows, maybe in the future, there will be a huge surge of funding related to, the waste processing area for application in whatever geologic repository we kind of decide on. I should say, though, there's plenty of funding in the waste processing arena. And I just think a huge, question mark there is where will the waste go? And I think there's a lot of politics involved in that sort of decision. If we're to talk about my specific research, I feel like so I'm not working on the waste processing aspect of, nuclear materials research. But yeah, I think in general, there will always be sort of, barriers or challenges in securing funding based on whatever political climate and whatever funding is available for different agencies. So this is, I work at a Department of Energy lab, but there's money coming from all over the place. This is not just DOE money coming here. And the way that people get funding can either, be enabled or made difficult based on, program manager decisions and, whatever is going on in DC that I might not know about. So I think a large part of research is obtaining funding that aligns with DOE missions, and then all the several agency or not agencies, but offices within DOE that fund, so you have to kind of be aligned to missions, and sometimes aligning yourself to these can be difficult.
Yeah. Wow. Yeah, no, I can imagine those are some intense challenges to overcome. And, and how can furthering our understanding of, like you said, having materials in a nuclear reactor is kind of the pinnacle of an extreme environment. And so how can furthering our understanding of how materials behave in those sorts of environments help us make, our fission reactors better, faster, stronger moving into the future?
Yeah, so I think something that is growing in popularity that isn't necessarily my area of expertise, but your question kind of reminds me of it. There are a lot of startups around the US and probably the world, I just know about the ones in the US, that are looking at different, reactor designs. And so there are a couple of things going on here. So any time we can kind of further our understanding of how materials behave in different environments, can help us predict how these materials might be performed when the reactor's operating. Right. So then we can kind of predict, okay, this is the lifetime of a reactor, something like this. But something that is also of interest is extending the lifetime, or maybe time between refueling cycles, things like this. And something that I am not really an expert in, but I think that could be kind of a growing area, is this small modular reactor design where maybe people, and I'm not kind of plugged into this community, but I would assume that refueling is not going to really be a thing there. It would be, where when I say refueling, commercial reactors typically do this refueling cycle relatively frequently. But if you were to create these small reactors that could be placed maybe anywhere around the globe where you might need high energy density, and that the kind of reactor, or what I'm imagining the kind of reactor you would like is to have a long lifetime where you're not constantly needing to refuel, right? So how can we go from using materials that maybe have a shorter lifetime to extending the lifetime safely? So, and that's where even just basic research on materials degradation might come in. But that's also critical to enabling new designs, because when you start to look at new coolant materials, new fuels, how are these materials interacting with each other and the environment? That is crucial to something like qualifying a reactor to even be built in this country or any country,
right?
For that fact.
So is that where you see like the future of nuclear reactors going, like looking at it, 10 years down the line, is just that extended lifetime? Is that kind of that main thing that you envision?
Well, I think that's a big push for a lot of designs and stuff, because refueling is expensive and not easy. And imagine a reactor where you build it once and you don't have to constantly maintain it like we are currently doing. That's a huge benefit, I think, in terms of, the output for the investment. There are also reactors that maybe can generate their own fuel. So again, that's kind of going to require less refueling. This is an interesting concept. Breeder reactor would be the term I'm thinking of. That's an interesting concept, again, because you can build a reactor that is, meant to provide power for 40 years. That's a long time. So to me, that's a huge goal for our future. But truthfully, I'm not, personally involved in any of those specific research reactor designs or areas. I just kind of, have learned about it here and there from reading or colleagues, etc. So I think that's a big future thing. But I also, we've talked about this a lot, but the waste processing, I think, is going to be a huge thing we need to overcome as a country before we can really adopt nuclear with, more open arms, so to speak. I'm not really sure. I didn't grow up during the Cold War, so what do I know? But I know. Yeah, right. I can ask my dad about it. I don't know.
Yeah, hopefully ongoing promising future for this space, most certainly. And so, bottom line for us, we've covered a lot today about this concept of nuclear materials and how they play into enabling this future of nuclear energy, broadly speaking. And so for our listeners listening to this, what are a few key points you'd like for them to take away about the impact of materials research in this space?
Yeah, that's a great question. And you've probably noticed I'm not the best at being concise, but I will try. Yeah, so I think, okay, first and foremost, this is very broad and applies to a lot of spaces, but I think fundamental research related to how materials behave in different environments is critical to not only, the future of nuclear energy and any nuclear materials application, but also just our future as a society, right? This kind of spans from nuclear energy to automotive, transportation, whatever. So I think research is really kind of the backbone there.
Yes.
And I was going to say something else. It'll come to me. I think the other thing that I want listeners to take away is that nuclear energy maybe seems a little bit scary because of, I don't know, I guess just kind of some just bad press.
Yeah.
But it's not scary. It's not different. I think, we were just talking about simple phase diagrams. It's a material science problem just like any other alloy design, when we were talking about fuels. And I think that with anything, knowledge helps you kind of peel away that
fear.
That's scary. Yeah, that fear. Yeah. So I would encourage anyone that's interested, or even just like a non-believer or doesn't think it's like the best energy source of our future, just to read and learn more about it. I'm constantly learning even, and I work in this space. So I think research and learning are going to be important parts of pushing nuclear energy into our future.
That's awesome. Thank you. I had very limited knowledge of this field, so I really did appreciate this introduction to nuclear energy and nuclear materials, and even you kind of removing or just playing your part in removing that stigma that there might be around this field. So we appreciate you coming onto our show. Like, we definitely learned a lot during this episode.
Thank you for having me. I appreciate it.
Thank you for tuning in to this episode of the It's a Material World podcast. If you enjoyed the show, consider subscribing and hitting the like button down below. If you want to meet other passionate material scientists and engineers, join our Discord community using the link in the description. If you have any feedback for us, we would love to hear it. We want to grow this show with our community's input, so comment below with your thoughts on this episode and what topics you want to see us cover next. We'll see you very soon, and in the meantime, go change the world.